Stats. This is chapter 3, day 4, and some of you guys won't be making it in next week, so I hope that you're able to stay up. So the end of chapter 3 is a little funky. It doesn't give us any real problems with this, but it does introduce the idea of dealing with a computer-generated data thingy thing. Okay, it's Friday. Don't judge me for my lack of words. So what we want to learn is to identify some very specific parts. This particular example that I've gotten off the internet gives us salary equals 24.8 plus 15.2 years. Now, what they're getting at here is they're giving you the form of a linear equation, where salary would be y hat, the 24.8 is the A, and the 15.2 is the B. The years is X in this particular problem. Now, if you look through the book, you're going to see that the book introduces this formula a little bit differently than we see in our calculator. It does it like this. Y hat equals B sub naught plus B sub 1 X. There's really no difference between these two, just they're using a different variable for it. And it makes it kind of confusing looking at it. So if you can translate the A and the B sub naught and the B and the B sub 1, you're golden. Alright, so what is all this junk? Well, to be perfectly honest with you, you don't need to know what it all is, but you do need to know a few things. So where did they get the 24.8 and the 15.2? Because that is our y-intercept and our slope. Well, they pull that out of this value here. This is the constant. The 24.8 is how much we're adding to everything that we do. That's the constant. The y-intercept is always a constant. And the years, although it doesn't say slope, constant kind of indicates y-intercept, but we've got constant coefficient, the thing that doesn't change, and the years coefficient. Well, coefficient indicates that it is the number that multiplies something. So the years coefficient would be our slope. So we have A and B. Now in all this other stuff, there's only two other things I want you to identify. And you should know what these are. S being the standard deviation, and R squared, RSQ, is your R squared value. Those are the only four digits I need out of that to pretty much say anything that I would say in, at least in this level of stats, to answer questions. So that is what I was hoping to show you. We will see more of that, I'm sure, later. I'm a little surprised they're introducing it this early in the book, but for those of you that are kind of maybe looking through the book, that's where that is and what that does. So where you would probably get a problem is you might be given just this information and told, if you're told to write a linear equation from it, or maybe to analyze some of the data. So you'd have to be able to recognize that this is the A, that's the B, the y-intercept and the slope, and then your R squared and your S. So again, we'll see more of those as the year goes by, but that's pretty much what you need to pull out. All right, so chapter 3, day 3. Day 4. A couple of the problems in the book that I give you today ask you to take some information and turn it into a linear equation. So we know that we can do our line reg a plus bx and it's done. And for the most part, that's what we're going to do. But let me show you what the book wants you to know. So if I go in to my lists here, for list 3 and list 4, I have that data that was from the Archaeopteryx. I keep coming back to this. I like it. It's small. It's linear. It works for us. So I'm going to use the femur data and the humerus data as an example here. So my L3 and my L4 will be my example values. So in the book it says that the slope of a line, sorry, zoom out here, the slope of a line, in our case B, in the book's case that's B1, equals the R value, that's your regression value, times S sub y over S sub x. Remember, slope is y's over x's, so this is the standard deviation of y over the standard deviation of x. So I'm going to take and get these values. Now I happen to know that R in this case 0.994. It's rounded a little bit, but it's rounded correctly at the thousandth. I know that because, well, we did that about 15 times, I think, or at least I did. So the standard deviation of x is going to be, how I can get that is a couple different ways. I'm going to use the 1-var stats, and I'm going to take L3, and I just want the standard deviation, this 13.2. So Sx equals 13.2. Now the calculator doesn't know when I'm using x or y, but I also want the standard deviation of the y values, which would be in L4. We'll call that Sy, just like the book does. So I want to get the standard deviation of L4. And that is, all I need is the 15 point, I'm going to call that 15.9. Okay, now, what I can do with that, oh, I'm sorry, I need two other values. I need the average of the x's and the average of the y's. So I'm going to put that out over here, x bar and y bar. I forgot to get that on the other one, but this would be my y bar, 66. I don't need that right now for the formula I've given you, but I'll need it here in a minute. And going back, get the average of L3. That's 58.2. So we'll hang on to those two. I don't need those right now. I need these three guys here. So I'm going to calculate the slope of the line of regression using this formula. So B equals 0.994 times the standard deviation of y over the standard deviation of x. And that is about 1.2. 1.197, I'm going to call that 1.2. Okay. So now I have my standard my slope of the line. How do I get the equation of the line? I have the slope, I have an x bar average and a y bar average. So think about our equation, y hat equals a plus bx. Well, I don't really have an x and a y value, but I have the average of those values. So what I can do then is I can use y bar equals a plus b x bar. So I'm replacing these values with our known averages of that set. if I do that, I have the b, I have an x bar, I have a y bar, and then I'm just solving for an a. So this is going to be 66 equals a plus 1.2 times 58, 58.2, getting ahead of myself on the decimal there. So let's see, if I'm solving this guy, 1.2 times 58.2 is 69.84. So 66 equals a plus 69.84. So if I subtract 69.84, I get negative 3.84. So now I have my y-intercept, which, remember, the book would call b naught, and my slope, which the book is going to call b1 if you go looking through the book. Then we have our equation of line. Y hat equals a, negative 3.84, plus 1.2x. Now, something that the book wants you to notice about this is that the r value is integral in the slope formula. It's part of the slope. So there are some interesting things about that. A kind of interesting thing, although I wouldn't call it an easy read, is figure 3.15 on in our book. I'll put this up here real quick. So in this particular example, they're talking about foot length and height, and I didn't use it as my example because it had quite a bit more data, but they're wondering about the difference here. What's happening is this is our mean of x and this is our mean of y. So I've got a couple lines here. This sort of, I don't know if that's purple or red, mean of x, and then a kind of a purpley one here, mean of y. And they intersect right here. And then I have the standard plus the standard deviation of x and plus the standard deviation of y. Now, the line doesn't go through the one standard deviation of the x and the y. It slips through a little bit underneath that. Why is that? Because it is the multiplier of r, which is going to be less than 1. So that is going to be some proportion of this distance. And that's exactly what this right here is doing. It's the proportion of the distance between those two standard deviations. All right, now we've done all that. I feel like I've done a little bit better job of explaining it than my A students. I apologize, guys. Today was a bit of a mess. We'll if you're watching this, we'll fix that when you come back. Now, okay, so how do we do that in the calculator? Well, we already know how to do that in the calculator, and I don't know really how valuable this is other than to understand really sort of where this stuff comes from. So if I was had a couple lists, I'd just put it in the calculator and go over and do my line reg calculation, but let's just see how close we are. I know there's some rounding, so I know it's not going to be just perfect. But what does the calculator do when it's asked to make that line of regression? We're a little bit different on the y-intercept. So my y-intercept is about negative 3.66. The slope was pretty darn close. I forget now what that number was that we rounded to 1.2, but I'd still round that to 1.2. I think there was 1.9 or 0.197 if I remember right. So the actual, without rounding, or without as much rounding, would be y hat equals negative 3.66 plus 1.2x. Now, how much different is that? I don't think that's going to create a significant enough difference to cause a problem for us. The point is we can get pretty close. We can get pretty close. And I think that in this example, again, I've mentioned that this example of the Archaeopteryx bones is convenient because of the size of the sample, but the reality is because the sample's so small, the averages and stuff are probably rounding out a little bit more than maybe they normally would if we had a larger sample. So anyway, I hope that clarifies some things. That should give you some heads up on problems 60, I think it's 63 and 65 that I've assigned. So anyway, look forward to seeing you next week. And if I don't see you before the break, enjoy it.